Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of B.Sc Physics Honours. Today we are dealing with the subject electronic devices. In this session we are going to concentrate semiconductor diodes. The topics that we are going to discuss today are P and N type semiconductors, energy level diagram, barrier formation in PN junction diode, current flow mechanism in forward and reverse bias diode, static and dynamic resistance. So, we are going to start with semiconductor basics, which is a must everybody has to know before going to know about a diode. So, semiconductors are devices in which the conductivity lies between the insulator and the conductor. Property of conductivity lies between the insulator and the conductor. That type of material is called as semiconductor. So, in the semiconductor type of material, LNG band diagram will be different than insulator and metal. So, in the picture that we can able to see the conduction band, which is lies always at the outermost part of in an atom, outermost part, and below that there is a valence band. And if we consider this is the topmost part of the valence band and this is a bottommost part of the conduction band, there is a gap between the conduction band and valence band. So, this conduction band and valence band, the gap present in between this is called as forbidden gap. So, that is represented by EG, energy gap, we also called as energy band gap or forbidden gap, and this is equal to 1 electron volt. It is represented in the electron volt because this electron volt, 1 electron volt will actually refers that how much of energy required for an electron to transfer from a valence band to conduction band. So, the basic principle is for a conductivity takes place only when the electrons, free electrons present in the conduction band. So, if the valence band electrons move to the conduction band, the free electrons will be present in the conduction band. This free electron is actually cause the current flow. So, and here the gap is very low compared to the metal and as well as insulator. In insulator, this forbidden gap will be too large, and in the metal this conduction band and the valence band is merged. And we are know with the definition of semiconductors, the conductivity lies between the insulator and conductor. So, the forbidden gap here is very small and it is not too large as in case of insulator and it is not merged as in case of conductor. So, this is the basic idea of energy band diagram of a semiconductor. So, in semiconductor there are two types, one is intrinsic semiconductor and second one is extrinsic semiconductor. And intrinsic semiconductor is a pure form of semiconductor. When there is no impurity is added for a pure semiconductor, that type of material is called as intrinsic semiconductor. And another one is extrinsic semiconductor, when impurities is added to the pure semiconductor material, that is called as extrinsics. And we can also know the example of semiconductor, that is silicon, germanium, selenium, gallium, arsenide, these are all the semiconductor examples. Next we move on to N type and P type. So, already we know the semiconductor there are two types, extrinsic and intrinsic. In intrinsic it is a pure form, we already know, and in extrinsic it is having impurities. Whenever the impurities is added, that type of semiconductor becomes extrinsic. So, extrinsic is again divided into N type and P type. Now, we are discussing about N type. Here the N type in the sense when a small amount of pentavalent impurity is added to a pure semiconductor, it is called as N type semiconductor. So, the impurity, the type of impurity added is pentavalent. In the picture we can observe that the silicon which is present here, which is having a valence electron of 4, and this is arsenic that we have taken as an impurity, which is combined with the silicon to form a covalent bond which is of pentavalent. But here is silicon valence electron is of only 4 electron, but arsenic having 5 electron, 1 electron will be left over. So, the electron, 1 free electron will be present in this combination, in this type of semiconductor. That is why it is called as N type. So, 1 extra electron will be formed with the adding of impurity like pentavalent electron. Like arsenic, if we add it for a pure semiconductor, will form extra electron. That is why it is called as N type semiconductor. So, and also this impurity that is going to form a free electron will also called as a donor impurity, because it is going to donate an electron. That is why it is called as donor impurity. Next, we move on to another type of a semiconductor, that is P type. When a small amount of trivalent impurity is added to a pure semiconductor, it is called as P type semiconductor. Whenever the small amount of trivalent we can say example gallium that we have considered in the picture. Again silicon is having a 4 valence band, and the gallium which is trivalent, the valence electron is 3. This shows an electron which is 3. So, one hole is formed. So, by the addition of gallium we are going to get an hole. Hole is formed due to the addition of impurities. Due to the impurity addition we get a hole formation. Formation of hole is formed due to the gallium impurity. That is why it is called as P type semiconductor. Example, whenever that impurities that we are going to add, which will going to makes or which will going to create an extra hole, that will be called as an acceptor, that will be called as an acceptor impurity, because it will be having hole which is creates an atom which can able to accept an electron. That is why it is called as an acceptor impurity. That is gallium, here it is called as acceptor impurity. And the trivalent atom that can be added for the P type material, example will be gallium, indium or boron. These are trivalent impurities or acceptor impurities that can be added for a pure semiconductor. So, next we move on to energy band diagram. Energy band diagram for an unexcited atom in a pure, that is intrinsic type of semiconductor that we are going to consider here. There are no electrons in the conduction band is first what we observed here. This is pure form. So, from extrinsic which is having P type, N type, by addition of impurities we can create holes and also the electrons, extra electrons will be created. So, that is the advantages of adding impurity for an pure, but here we are studying only intrinsic energy band diagram, that is where we do not find the electrons in the conduction band. So, this is how the energy bands would be. This is energy band which one, that is a shell one, it is named as shell one, which is very near to the nucleus, and above this there is second band, third band, which we consider as a third band as the last or outermost band, it is considered valence band, and above which will be the conduction band will be there, and here conduction band valence band will be there where the electrons is present. Because of intrinsic property, that is a semiconductor here that we consider for energy band diagram study is intrinsic. So, we do not observe any electron on the conduction band, and in between this the band gap, that is a forbidden energy band gap or forbidden gap, that is what we already studied in energy band diagram of semiconductor. This is present in between conduction and valence band. Next we move on to conduction electrons and holes. So, the same that intrinsic semiconductor property only that we are going to studying here also. Here we are going to study about the how the intrinsic semiconductor behave at a room temperature. Even though in the room temperature there are no free electrons at in the conduction band initially, but due to the temperature, so due to the absorption of temperature that is present in at room temperature, that energy, the temperature or the energy absorbed from the electrons present in the valence band, which will going to absorb the heat energy that presents at a room at the room temperature. The temperature, that is the heat energy, is absorbed from the electron that is present in the valence band. So that heat will going to absorb by any type of electron that will going to eject the electrons from the conduction band, from the valence band to the conduction band. That is what we observe from this picture. So before it is present in the valence band only. At the room temperature, when the heat energy is absorbed by this electron, it will going to eject and become a free electron and leaving behind the hole here. So this is how the electron will be ejected at the room temperature also in the intrinsic semiconductor. And another property that we need to study about intrinsic is a recombination. That is, whenever the electron is ejected from the valence band and it is moved to the conduction band and leaving behind the hole. This is what we studied. So when it is moved to the conduction band, there is a free electron present in the conduction band and the hole is present, that is in the valence band. This forms a electron hole pair. That is why it is marked here. This forms electron hole pair. And one more thing, after it does not stay for too long here in the conduction band. After whenever it loses the energy, the free electron present in the conduction loses the energy, will come back again to the valence band. That is called as recombination. Whenever the electrons, free electron present in the conduction band loses its energy and come back to the valence band, it is called as recombination. Next we move on to charge carrier concentration in N type and P type semiconductors. The free electron and hole concentration are related by the law of electrical neutrality. That is we need to know this concept for upcoming derivation and all. So what is the charge concentration in N type and P type? So the total positive charge density is equal to the total negative charge density. That is the basic that law that we consider, that is electrical neutrality. The positive charge density is equal to negative charge density. So here by electrical neutrality, it will going to define that Nd plus P is equal to Na plus N, where Nd is the concentration of donor atoms, that is number of positive charges per cubic meter contributed by donor ions, that is the donor atom concentration of donor atoms, and P is the hole concentration and Na is the concentration of acceptor atoms and N is the electron concentration. So according to law of electrical neutrality, Nd plus P, that is always equal to Na plus N, that is positive charge density must be always equal to negative charge density. So for N type, if we consider this, what happens for purely, if we consider for N type, what happens? So Na, if we consider Na is 0, because for N type there is a presence of Nd, donor atom will be present in a N type semiconductor and there is no acceptor atom. So that is why Na is 0, that is concentration of acceptor atoms N type materials will be 0, and also the number of electrons in the N type, that is a majority carrier always in N type, is more than the P, that is hole. So and the neutrality law now becomes Nd plus 0 is equal to 0 plus N. So then we can able to find this Nd is equal to N, that is donor concentration of donor atom, that is equal to number of electron that is present in a N type semiconductor. This is what we found, and also we can also come across the mass action law that defines as Np, that is equal to Ni square. This is the intrinsic carrier concentration. This is the number of electron, number of holes that equal to square of intrinsic carrier concentration. That is what the mass action law defines, and this can also be written like this: P is equal to Ni square divided by N. That can be divided, that can also be rewritten as Ni square, where N is already we know here, that is equal to Nd, that is the concentration of donor atoms. So, the concept that we studied it for N type, we are going to implement the same concept to the P type semiconductor. Here the Nd, the donor atom, that is here for P type the donor atom is concentration will be 0 here, and also the number of holes is much greater than number of electrons. So, again the electrical neutrality law will becomes Na plus 0, that is equal to 0 plus P, where Na is equal to P, where that is that states that number of holes is equal to number of concentration of acceptor atoms. So, also the same thing that we need to apply this for mass action law, where number of electron and holes is equal to intrinsic carrier concentration square. So, this can be rewritten as N is equal to Ni square divided by P. P value can be substituted as Na, which is known for a P type semiconductor. So, next we study about energy diagrams of the p-n junction and depletion region. So, this is very important concept. So, we come across a P type and N type. So, we are moving towards the diode concept now. From the semiconductor concept to we are moving towards the diode concept. We know the P type material and N type material. How the P and N type material will be formed we know, but we do not know what exactly the energy bands in the P and N type. So, when the P type material is brought near to the N type material, the junction is formed. So, the behavior or energy band diagram, that is what previously formed in a P and N type, will be slightly different in when the junction is formed, when the P and N is come into contact. So, this is what the P-N junction, that area here it is represent the P-N junction here, and this is P type semi region and this is the N region, and we will come first with the instant when the injection, at the instant when P and N type material is come into contact. So, the very firstly when the P and N type material is come into contact, this is how it looks. If we know that for a P type material, the conduction band here and the valence band will be here. If we taken like this, if when it is come into contact in the P type region, the minority carriers will be electron and the majority carriers will be holes always in P type, and in the N type the minority carriers will be holes and the majority carriers will be electron. And also another thing that we need to know is due to the potential gradient, that is from electrons have a property that it is always move from a higher potential to lower potential, that is called as potential gradient. So, here the N type region will having a more number of electrons in a conduction band. So, it is trying to move from N type region to P region, N region to P region. So, the N region electrons will going to move to the conduction band of a P region, which can be appeared here. This is what the process is called diffusion. Due to the potential gradient, the electron moves from N region to P region, it is called as diffusion. So, initially this electron flow will be happen. Similarly, the majority carrier present in the valence band of P region will move to the N regions due to the diffusion and potential gradient, and due to this it is going to move, the electron holes will going to move across the junction like this. And how long this will going to happen, we will come to see at this point. When all the electrons will move to the P region and all the holes will move to the N regions, there will be a drift present here. So, due to the equilibrium, there is a equal and opposite forces that will be built. Whenever the equal and opposite force build, there is a depletion layer is formed due to this. There will be a depletion formed due to this, because when the electron flow from N region to P region, electrons leaves behind a positive donor atom in the N region, and also the holes when we move from P region to N region leaves behind the negative acceptor ion in the P region. So, this will be forms here, this will be present in the P-N junction, and it is going to form a depletion layer. So, this will going to form a depletion layer and it does not allow any more flow of electrons and holes due to this presence, because as electron and holes initially moved, this depletion layer was not present because of potential gradient. It will going to move the electrons and holes across the p-n junction. At certain extent, there is no further movement of electrons and holes in between the junction due to this depletion region formation. Whenever the electrons and holes stop to cross the p-n junction, by that time it is called as the p-n junction is depleted. So, next we move on to another concept that we know the depletion region. It is formed due to the presence of acceptor atom and donor atom that is present in a p type and n type respectively, and here we can observe this is initially when the instant at formation of junction is formed, that is the p-n junction is present here, and this is when the depletion region is formed, and the direction here which represent the electric field is produced due to the movement of electrons. So, this atom, that is a donor atom, positive donor the atom that is present in n region, and negative acceptor atom that is present in p region, this will going to form few more layers like this, and it will going to increase in such a way until the no more electrons and holes will cross the p-n junction. At that time it is called as depleted, the p-n junction is depleted, and the area it is called as depletion region. And due to this depletion region, there is a change that what we observed here in the energy band diagram. There is a slope we observed here. This is due to because of a change in an electric field, because here it is flat, the electric field here and here it is same, it is not change here, that is why there is no change of electric field. Here the electric field is slightly changed. Due to this, there is a potential differences will be there, that potential is called barrier potential. So, this depletion region will become a barrier, so that no electron and holes will cross this p-n junction. So, that is why it is called as the field that is created in this depletion region or barrier is called as potential, barrier potential. So, next we move on to a very important topic, that is the p-n junctions. We know the property, this how the electron and hole is move across the p-n junction, how the depletion region is formed, and also how the barrier potential is formed in the p-n junction. So, now we study the p-n junction and its properties with this picture, where we know that there is an electric field due to the presence of depletion layer and the acceptor atom in the p region and the positive donor atom in the n region. So, there will be sufficient electric field will be present here, and also this will going to indicate the potential difference across the junction will be like this. This is the potential difference that we can observe in the depletion layer, and due to this depletion layer potential difference, there will be no movement of electrons volt across this. So, due to the diffusion, the energy holes it is moving away from the n region, and the electrons it is also moving from away here, because the depletion region it is making such a way that it does not allow the any movement or any flow of electron and holes across the p-n junction. So, next we move on to the two different modes of operation of p-n junction diode, that is one is forward biased, another one is reverse biased. So, very first we need to know what is biasing. Biasing is giving a potential, or whenever we are going to connect the source or whenever we are going to give a supply, that is called as a biasing of a p-n junction. So, till now we did not give any supply to the p-n junction studies, we studied with the respect without giving a supply, we studied till now the properties and what are the characteristics and how the electrons and holes movement and also the formation of depletion layer and barrier potential formed inside the p-n junction. Now, what happens when we are going to give a power supply to the p-n junction? It is very interesting. If we are going to connect p-n junction in such a way that is a p region to the positive terminal of forward biasing voltage and the n region to the negative bias of the forward biasing voltage, this form of connection will leads to a forward bias of a diode. So, this is a circuit symbol that we can represent with the help of series resistance, and this is a diode symbol. Here this is a positive and this is a negative sign with negative terminal, this is a positive terminal, this is a negative terminal of a diode, and this arrow mark always indicates the direction of current, and this positive is connected to the positive of voltage supplies, and the negative is connected to the negative of the supply voltage. So, this is how the forward bias junction can be formed with the help of a resistor and also supply. So, when the forward bias voltage is given, so it is very interesting, the depletion, very firstly thing that when we are going to give a supply, it will going to affect the depletion layer here. So, what happens when we give the supply here? So, when the voltage is applied, the depletion layer that is already formed will be going to reduce. So, due to the reduction of this, the electrons present in the end region will going to acquire the energy, and whenever it acquires the sufficient energy to cross this p-n junction, will going to cross this p-n junction, which is become very small, and due to this flow of electron, the current will flow in the diode. So, this will be going to help in the conduction of electricity. So, the current will be flowed in the forward bias, and the forward bias current is called as forward current, that is IF, which is represented as IF, and in the picture this is how the electron and holes will be moved across this. So, whenever the potential, that positive electron is given, the electrons present in the p region, that is also moving here, because the p positive terminal is connected with the positive terminal of the supply is connected to the p region, and negative terminal is connected to n region. So, unlike poles like attracts each other, so the electrons present in the p regions will comes near to the p terminal, and also the holes that is present in the n regions, that is comes to the n regions, and here also from n region also the electrons is moving here, and also the holes will move in this direction, and this will going to produce a current flow. So, next we move on to the forward characteristic curve for a junction diode. So, we know how the current will be flown when the diode is in forward bias mode. When we are going to give a supply, when the positive terminal of supply is connected to the p region and negative terminal is connected to the n region, the current flow will be exist in a diode circuit. And this is how, when we are initially the voltage change is made, the current change is very low initially till 0.7 volts. So, after 0.7 volts, as the voltage the change in voltage is less, the current is changed abruptly. The increase in the current is, we can observe here, the increase of the current is very high here, and even for a small voltage the increase of current is high here. And this point where the current changes abruptly, that point of voltage is called as potential voltage, or also called as the cut-in voltage or knee voltage. We can called it as a knee voltage. This is 0.7, usually it is a 0.7 voltage for a semiconductor of which is having a material, a silicon material. It is a 0.7 volt, and this is called as knee voltage. So, this is what the forward characteristics, which is for a minimal change of voltage we can observe the maximum change or increase in the current. We come to the end of this session. Let us have a quick summary. In this session we come across the basics of semiconductor, that is semiconductor's definition, how the energy band diagram of a semiconductor, and also we come across the different type of semiconductor, that is intrinsic, it is a pure form of semiconductor, and extrinsic, it is having impurities for a pure form, is called as extrinsic. And also in extrinsic there are two types, one is p type and n type semiconductor. So, with all this basic knowledge we move towards the diode, we move towards the diode concept. When the p type and n type semiconductors are joined together, it will going to form the p-n junction diode. And also we observed the depletion layer formation and how the electrons and holes are responsible for the depletion layer formation, and also the potential difference or the potential barrier potential is formed due to this diffusion, that is also we come across in this session. So, some of the questions of this session are: how is an n-type semiconductor formed? What is the majority carrier in an n-type semiconductor? What is the difference between intrinsic and extrinsic semiconductors? Explain what the barrier potential is and how it is created. This ends the session. Thank you.